तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We continue the discussion on 3D viewing, pipeline and projection transformations under the category of 3D viewing. And in the last hour of lecture, you remember that we have discussed basically the viewing pipeline in the terms of 4 different stages of transformations, and within those 4 we in fact exclusively discussed only one of the stages, the important stage of normalizing transformation. So, if we look back into what we were doing in the last 1 hour, implementation of 3D viewing, the input to that is 3D world coordinate output primitives, and which passes through 4 stages of transformations. The first one is to apply the normalizing transformation. The second is to clip against the canonical view volume. So, we know what is a canonical view volume now, and then of course comes the projective transformation or project into the projection plane, which will actually take the 3D to 2D, the coordinates, and then transform into viewport in 2D device coordinates for display. And so, the output of this entire set of operations, or in some sense the viewing sequence or pipeline, is the 2D device coordinates. And if we look out of these 4 stages, we mainly discuss the first one, which is the applying normalizing transformations, which consisted of 5 different steps of operations, or 5 different matrices to be which were doing these operations on the 3D world coordinate output primitives. We knew what is a canonical view volume. When we read about and understand and discuss about clipping, we will see how the clipping operation could be done, because that you always when you have a graphics display, or when you in fact seeing through your eye, you have always a finite amount of display, and you need to clip and throw out the world which is outside the range of viewing, either through the camera or through the eye. And of course, in 3D transformations, we have also studied projection geometry, the M generalized matrix. So, we apply that, and the last step is a 2-dimensional simple transformation, which we will also see today. So, the first stage, if we look, which is the applying the normalizing transformation, and we had seen 2 different projection transformations, one under the category of parallel or orthographic projection, orthographic or non-orthographic in case of parallel and perspective, and these were the 5 different stages for the normalizing transformation in terms of parallel and perspective. So, just to have a comparative study, you remember we had a translation matrix first, because the operation is going from left to right. So, we are talking about pre-multiplying the matrices or coordinate points by these operations. So, translation minus VRP, then a rotation, then again a translation or a shear, and then a scale ultimately. So, that's the combination. The sequencing is very important. You cannot jumble up, because we have studied under transformations that order is very important. Sequence of operations are to be kept unaltered to have the correct projection or the transformation done. And out of these 5 operations, the most crucial one was probably the rotation matrix R, where we first transformed a coordinate system, a view reference coordinate system, onto a world coordinate system. We knew how to align that using the property or orthogonal property of the rotation matrix, and also we discussed about shear and scale the form of those matrices. Okay, couple of exercises were given to you during that time to identify the parameters of shear based on the direction of projection vector and scale parameters for the scale matrix for parallel and perspective as well. Both are of similar types. The shear matrix is optional in the case of parallel projection if it is pure orthographic, because the direction of projection in case of orthographic projection is aligned with the view plane normal. So, you do not need a shear, but if it is not, you typically will need a shear. Okay. So, this is the first stage of that pipeline, the viewing sequence of 5 different steps of the first stage. And then of course, after the clipping has been done, you can apply the projective transformation. This also we seen a few classes back when we were discussing about 3-dimensional transformations, and I talked about the generalized expression of the transformation matrix M general, and it depends on basically mainly 3 key or 4 key parameters. One is the ZP, the distance of the projection plane from the origin, and also the direction vector dx dy dz, which consists of the direction of projection vector and the length of the point COP or PRP from the point 0 0 ZP is Q. We know that, and we had seen the derivation of this matrix as well a few classes back. Okay, so first, second, third stage is clear, and the fourth stage of course is a simple 2D transformation. So we look into the pipeline in a slightly different framework now. We look through a slightly different framework where we talk of coordinate systems and matrices together for this entire 3D viewing pipeline, a sequence of projective transformations and world coordinate systems moving together, and we see from how do we move from the 3D object coordinates situated somewhere in space, and then you have a camera looking through it. Your world coordinate system could be somewhere here, a right hand or a left hand system, your object points could be somewhere at this point, the camera looking this way. So what will you see in the graphic screen when a camera is located at an arbitrary point looking in the direction at some arbitrary direction? You have a set of objects at this point, and the world coordinate system is somewhere here. VRC is aligned with the camera, is looking down, objects are somewhere here. Objects which could be outside and away from the camera will not be in the field of view, because you have a finite zone or a field of view both for the case of parallel as well as the perspective projection geometry, and you need to transform all these points from 3D into the canonical view volume, transform the VRC into the world coordinate system, then do the projection geometry from 3D to 2D and get into the viewport. Okay, so that's a sequence of operations which are taking place for a generalized scenario. Of course, you can have a very simple scenario to start with. If you say my camera is looking in such a manner that it's pointing towards you or towards me, and the world coordinate system is also aligned with the camera, it becomes very easy, because most of these transformation matrix will be unnecessary. You will not need them to be used in your normalizing transformations, and you can simply worry about the camera parameters and the world coordinate points which are to be displayed on the screen. Of course, we will see such a simplified model which is only based on a camera, but a generalized scenario is very, very important, because in a generalized scenario most of these graphical softwares based on FIGS or OpenGL will ask you to specify a viewing pipeline, specify the viewing scenario, where you have to specify what is your world coordinate system. It could be somewhere placed on the earth, on the universe, on the sun, wherever it is, and then you have the camera located at some point with respect to this world coordinate system. The camera is looking in a particular direction. You have a set of objects somewhere positioned here, a set of points, lines, surfaces, curves, text, whatever the case may be, and you would like to have this generalized scenario so that you can handle all sorts of environments, not only the simplest case. The simplest case cannot handle generalized scenarios with respect to a camera model, which we will see later on, and most graphical software, when you talk of the programming language layer or the higher level FIGS standards, it asks you to specify certain parameters for the viewing pipeline or the projection geometry. So we'll come back. Of course, always keep in mind that there are two main type of projection geometries. One is the perspective geometry and the other is the parallel geometry, and again we start with the 3D modeling object coordinates. 3D modeling object coordinates they go through a modeling transformation. That's the first stage. You have the modeling transformation, where basically what you do is it generates the corresponding 3D world coordinates for the object model, because you may have 3D modeling object coordinates with respect to an object center, and you need to position them somewhere in the world. In the world, and that is what we call as the 3D world coordinates generated by the modeling transformation. In this case, the modeling transformation talks of positioning those objects and the points and lines, curves, surfaces of the object at somewhere in the universe or somewhere in the world. So you get 3D world coordinates, and then you probably start to give the transformation, which we will call the normalizing transformation. We break it up into 2 or 3 different parts. The first part of that is called the view orientation matrix, where you can see the expressions are given on the left hand side corresponding to perspective and parallel. They are basically same. In fact, they are nothing but the first two steps of the first stage of the normalizing transform. That is the translation vector, put the VRP to the origin T of minus VRP, and then the rotation matrix which will align your view reference coordinate system with respect to the world coordinate system, which is our origin of the overall system. So that is the view orientation matrix, which takes the first two steps of the overall 5 different steps of the normalizing transform, and the flowchart is not complete here. It's so big that I split into 2 parts. So after the view orientation matrix, we move on to the next slide which talks of the remaining stages. So the view orientation matrix has the R and T matrices, and it will generate what we call as the view reference coordinates. Okay, so the dark black boxes talks of the matrices, and the elliptical areas talks about the coordinates at different stages. Okay, the outputs at different stages. So if I go back, you started with the modeling object coordinates, you move to world coordinates. After that, the view orientation matrix will generate what we call as the view reference coordinates, and then on the view reference coordinates you apply what is called the view mapping matrix. You apply the view mapping matrix, which has all the remaining 3 steps of those 5 different steps of the first stage of normalizing transform, that is the translation and shear and the scale. Okay, so you have the T, you have the SH and the S matrices. Now in terms of perspective and parallel, if you see, I have tried to minimize the difference by saying that I will have a M matrix which will probably make my S bar is equal to appearing like S bar. The scaling could be little different in case of perspective and parallel transformation, because the canonical view volume is different. That is why the extra M has come to take care of the same and give you the difference between perspective and parallel. Otherwise the shear and the translation are typically of the same type. Okay, so after that, after the view mapping matrix has been applied, from the view reference coordinate you get the normalized projection coordinates, correct? The view orientation matrix generated the view reference coordinates, and the view mapping matrix generated the normalizing projection coordinates. In fact, the view orientation matrix along with the view mapping matrix were those 5 different steps of the normalizing transform which we had discussed in the last hour. So those 5 steps have been split into 2 parts, 3 matrices, 3 steps and 1 in 2 steps, and they are called here the view orientation matrix and the view mapping matrix respectively. Expressions are given for the view orientation matrix here in this slide, that is the T and the R, and the rest of the translation, shear and scale is a part of the view mapping matrix, and it has generalized and it has generated the normalized projection coordinates. These normalized projection coordinates are still, I will say, in 3D. You are still in 3D, but now what you have done basically is, if the objects were somewhere here, this was the world coordinate system, the camera was looking here, you have actually done the following by transforming the camera, getting it aligned with the world coordinate system. So the objects are now also followed the same path, and you have actually shrunk the entire view volume, parallel projection geometry, into this small canonical unit view volume, okay, which is bounded by 6 planes. We know the CVV, canonical view volume, bounded by 6 planes, top, bottom, left, right and front and back planes. Okay, so now the entire world which you are supposed to see through the camera at some point is now all aligned and kept with the world coordinate system, and it is all inside the canonical view volume or inside the CVV. But the points are still in 3D. They are still in 3D, but in a well bounded or well defined normalized projection geometry, and you have to apply basically 2 or 3 different steps. The first step is clipping. First you have to clip with respect to the canonical view volume, then apply a projective transform, and then do a transformation in 2D. That is all put under one category in the last stage of the viewing pipeline, which I will call as clip, transform into 2D screen coordinates, transform into projective from 3D to 2D, and then shift it to 2D screen coordinates, and all those put together except the clipping part, I say, is all handled by one particular big matrix called MCVV3DVP. I will explain what this means, but this matrix after clipping, when it is applied, will basically give you your 2D device coordinates. Now this MCVV3DVP is basically meaning canonical view volume 3D viewport. Okay, that means it's a transformation matrix M which transforms the canonical view volume into your 3D viewport for projection. So this has to be done after clipping, which will transform, and then you can apply your projective geometry matrix M general also to get the 2D points from the 3D, and it will give you your 2D device coordinates. Of course, you may need a little bit of scaling and translation at the end to get the 2D device coordinates within the viewport you are talking about. Okay, you need to map everything into a viewport, which we talked about earlier, and this is all coming under the category of MCVV 3D viewport. That's a terminology used in one book by Foley, Vandam, Rogers, and etc., where they will say that we have a this is a matrix called MCVV 3D VP. It means canonical view volume to 3D viewport, and the expression of that matrix is given here. And this matrix you should apply after clipping. After clipping, when the entire 3D canonical view volume has been generated, all points under that, you apply basically clipping, then apply this matrix. As you can see from the expression, the MCVV 3D VP canonical view volume to 3D viewport consists of a translation, scale, and a translation. So basically what it is doing, it is trying to adjust the canonical view volume to your 3D viewport such that you can actually apply your M general projection matrix to get the 2D points out of 3D. Remember, these are 3D matrices again, the world is still 3D now. After doing all 3D manipulations necessary, you basically apply the projective transform to create your 2D coordinate points from 3D. So clipping, apply MCVV 3D VP, then apply M general to create your 2D coordinates, and then of course you have to do a little bit of scaling and translation to position all whatever you want to see in a particular viewport. If this is the screen which you are seeing right now, you will say, okay, I don't want to see all the text in the entire screen, I would like to select a small portion here or maybe some portion here. So that is what is a 2D viewport. I will say all I want my display on this particular graphics package to be positioned here or somewhere here. That is what we will call as a viewport, and what you may need to do is the 2D device coordinates which will be generated with respect to the whole setup. You need to scale it down and then translate it and position in the viewport which you demand or the user asks. So you need to map it into a 2-dimensional viewport. Those expressions are very simple. Since you all know how to do 3-dimensional transformations, 2D transformation should be very simple. A simple scaling and a translation brings you from this entire screen down to a small viewport, because you have a big screen, then you basically do a small scaling operation to bring it down, and then you can position it anywhere in the screen, basically the viewport through which you are viewing the world which you decided, and that is a simple translation operation. So you at the end basically you will require a scaling and a translation in 2D, which is not there in the expression, but you can visualize that it comes at the end after all the projection geometry is done, after all the operations of normalizing transforms of the viewing pipeline, after the clipping, after the M3V CVV to 3D viewport, and then after you do the projective geometry M general matrix to transform from 3D to a screen 2D, and then now you want to position this screen, because you may not like the entire display screen to be covered by just one window of graphics screen. You may have a graphics screen here, you may have a multimedia operation, some text running here, and some other operations down below. So obviously you will not ask one particular application to cover the entire screen. So that entire device coordinates where you want to display will be generated by a 2D scaling operation and then positioned by a suitable translation. So that is the viewing pipeline which we have talked now, and again I will repeat this in steps. To complete the entire 3D viewing pipeline, we can also take a scenario where it involves not only this transformation, but of course you need to generate pictures. You need to generate pictures with the help of different algorithms which will come in due course of time as we go along in terms of shading, drawing lines and things like that, and we will discuss in general now the various steps of what we have seen to the, now we will say a very elaborate or a very general 3D viewing pipeline. And most of these operations you know, the objects are modeled in object modeling space. That is the first step, you know that. Okay, so you have an object centered coordinate system, and objects are centered or modeled or kept somewhere in the object space, and then you have to actually apply a transformations which will be applied to the objects to position them with respect to the world space or the view reference coordinate system, at least with respect to the camera coordinate system or world space or world coordinate system WC or VRC, that is view reference coordinate system. You would have to apply transformations to keep this object. So the second stage says transformations are applied to the objects to position them somewhere in the world space. Okay, so that is important. View parameters are specified. We had seen in the earlier class a table with a few examples of what are the different view parameters you need. A typical set of examples you can think of are, yes, you need to specify, say, the view plane normal, which direction you are looking. You need to specify the view of vector. Let us say you will also need to define other parameters for the viewing system, but typically at least you need to have the view up vector and view plane normal, view up vector and the view plane normal to specify the world coordinate system. And there are other you can look back into the table which was given in the previous class to have examples of different type of perspective and parallel projections and view specification. So that is all necessary now. That's the third step where we say the view parameters are specified to define the view volume of the world, a projection plane. Of course, you need to tell where is the projection plane and also the viewport, the two-dimensional viewport on the screen. So these are some of the parameters could be optional, but you need to specify at least minimum some of these parameters to specify where you are looking. Correct? You can have a world, you can have a virtual reference coordinate system, but you can have a camera looking from this angle onto the object or from this angle or from, so you need to specify your where is your camera and what direction it is looking. Of course, if the object is here and the camera could be looking somewhere else, you will not be able to see anything unless there are objects somewhere there, but typically you need to position it so that you want to see what sort of view you would like to have. Would you like to have the top view or the bottom view of an object? If this is an object, let us say, or the side view or the front view. So you need to position your camera, you need to specify the viewing reference coordinate system with respect to the world coordinate system here, you know where the object is placed. So all these viewing parameters are very, very important, which talks of a general three-dimensional viewing pipeline. So I repeat again these steps. The first step was the objects are modeled in the object space or object modeling space. Second, you apply your transformations which are applied to the objects to position them somewhere in the world space, and then you specify the view parameters which are specified to define the view volume of the world and the projection plane and the viewport on the screen. So these are the first three stages of the viewing pipeline. Then once the transformations are applied, you of the projection geometry and all normalizing transforms are available. The 5 different steps which we talked about, rotation, translation, shear, scale and all that in 3D, you need to clip this object with respect to the view volume. Now actually sometimes the objects are often clipped with respect to the canonical view volume, because the expressions for clipping actually become very simple when we use with respect to the canonical view volume. You remember the expressions of the 6 planes which bind the canonical view volume both in the case of perspective and parallel. There were 6 planes and there were 6 different simple expressions. You can almost visualize it: x equal to +1, x equal to -1, x equal to y, x equal to -y, z equal to -z min, z equal to 1 and so on. So if the expressions of those planes are so easy, it helps you to make the clipping algorithms work very fast. Almost you can get a closed form, very nice expression to obtain the clipping. Clipping means what? You have a line and you have a bounded volume within the through which you are seeing this line, let us say. So of course what it means is, if this is your view volume and the line is somewhere inside, you will not be allowed to see outside the view volume whatever the line exists. Remember, it's a virtual world. A line or a rod can actually go through any particular material. So if you have a virtual volume, you will be allowed to see only inside of it, and that is where you require to clip the line and come out with only that section of the line which the graphics screen should be displayed on the graphics screen, not the outside. And the expressions for this clipping becomes very simple when you operate with the canonical view volume, because the canonical view volume has very simple expressions for the planes which bind the canonical view volume. But of course generalized expressions are available for clipping, in which you can clip actually in any 3D space with any arbitrary view volume. That's also possible. So you either clip with respect to the view volume prescribed by the viewing geometry, or you clip with respect to canonical view volume. Okay, so after the clipping is done, then the results are projected onto the projection plane window. So this is from 3D to 2D, and it's finally mapped into sorry, this is still in 3D, it is mapped into the 3D viewport. So it is something like the canonical view volume comes into the picture, and it defines a small 3D viewport through which you are able to see the entire world. The entire world is squeezed into a canonical view volume and 3D viewport. Okay. In this 3D viewport, you are still in 3D, remember. Before going to 2D, if it is a simple case, then you slightly apply the projection geometry and go from 3D to 2D. Otherwise, what is done is, in a case of complicated structure like a house or any complex building or environment where there are lots of objects and each object has a lot of surfaces in the front, back, side and all that, you need to remove certain hidden objects. Now this is a special, there are specified very good algorithms to do this particular task of removing hidden objects, hidden surface removal algorithms, which we will see. So we will see what is this hidden objects removal. It is now, for the time being, you can assume that if you are the camera is looking towards me, let us say in this specific example, you are not able to see your back. Even when I am looking at you, I am able to see your frontal face and maybe the side, but may not be the back side. So this back side of yours and my back side are all objects on the onto the back of mine, or they are all hidden. They are all hidden. Notionally, you can visualize that, and there is no point drawing those on the screen, because anyway I will be overlapping these objects and you will be overlapping whatever is behind you. So you need to eliminate those or remove those hidden surfaces from the scene in terms of drawing it on the screen, because otherwise you will spend a lot of time, waste a lot of time in drawing those. So hidden surface removal algorithms are very, very essential, very important to reduce the computational complexity of drawing objects. In fact, typically what is found that almost in most of the cases 20 or 30%, or at the maximum on an average 50% of the surfaces is what you need to draw for a general 3-dimensional scenario, and that's why, and it is made possible with the help of hidden surface removal algorithms where all the hidden surfaces are removed. So you need to have that in the graphics weaving pipeline as well, and so the hidden objects are then removed, and then when the hidden objects or the hidden surfaces, lines, etc., all are removed, you only are left with the objects which are now visible to the camera, visible to the user, and you want to show those objects, render them. So the objects are what are called scan converted and then shaded if necessary. Okay, now that means we are talking of two more types of sections, methods or algorithms which are dealing with scan conversion and shading. So along with hidden surface removal, after that we will also have to study about scan conversion and also shading algorithms to find out how to effectively not only shade objects, but if possible and necessary create shadows. That's very, very important. So we will study, but we can say that this is under the general category of 3D viewing pipeline, which you need rendering algorithms are necessary under the category of general viewing pipeline as well. Okay. So, we'll look at again from a flowchart angle. When you have the flowchart of the 3D viewing pipeline, you have the object model which creates the object space. Then under the object space you scale, rotate and translate the objects, generalize transformations, you go to the world space. In the world space you specify the view, calculate the surface normals, calculate illumination, remove the back faces. We had seen a few of these terminologies now. We will look into all those algorithms as we go along in this sequence of lectures, and you are still in the world space. After you specify the view, calculate the surface normal, calculate the illumination, back face, etc., and then you apply the normalized transformation and clipping to create, go into the what we call as the I space, go into the canonical view volume 3D viewport from the world space. Okay, and this again the flowchart is not complete. We are giving the general steps of the 3D viewing pipeline. We gave it in steps. Now I am giving it in the flowchart again, and and where you know where the matrices to be put, and after each matrix operation which space you are talking about. So we have moved from world object space to world space to I space, and from I space is where you apply your projective transformation or projection transformation matrix or parallel projection transformation as the case may be, and there is where you move from 3D to 2D. You move from 3D to 2D, and that makes you move from the I space in coordinates to the image space in 2D, and there is where you can apply the hidden surface removal algorithms in the image space, or you can apply it also in 3D space as well, and there you provide the shading, the texture, all that is necessary for drawing the objects. Then you map into the viewport. You map it in the viewport and draw the screen. We talked about this viewport on the screen because you may not be, it may not be necessary, and you may not want to draw the entire picture on the entire screen. If it covers the entire screen, you may not be. Today we talked about a dynamic environment with several users, several tasks in a multitasking, multi-programming environment where you will not be having graphics programs, but other programs also running in a system, and you may have also multiple graphics programs. One of them could be just rendering a scene with a house or some building structures and all that. You can have another graphic screen displaying a movie or a multimedia animation and stuff like that. Another could be doing giving a visualization of a multimedia of say molecular biology or some other visualization of computational fluid dynamics or some other engineering CAD/CAM applications, let us say. So you need, of course, not always the case that you complete the entire screen should be complete with one graphic screen. You define your viewport and display. Put the size of the viewport depending on the demand of your application. You can always scale the viewport if necessary and pull it up to cover the entire screen and then bring it back. That's all right, but you always need to put it on a viewport. So you map to viewport and draw the raster on the screen, and that generates the device coordinates. As you see on the screen, as you see on the last step of the flowchart, when you map into the viewport and draw on the screen, the corresponding device coordinates are generated. The corresponding device coordinates are generated and they come through starting from the object space. So, I go again object space, world space, eye space, image space and ultimately the device coordinates. Where within the viewport you want to draw your graphic objects is now specified starting from an arbitrary three-dimensional world where the objects were given. Objects were here, camera was at some position, world coordinate somewhere, it has gone through all transformations, clipping, 3D to 2D, hidden surface removal, shading, all that algorithms, and finally you have it in a viewport. You have in a viewport the objects which are drawn, which the camera is supposed to see on the objects. You change the objects, the position of the objects, or you change the camera position by altering the 3D view specifications, whatever is being drawn in the viewport will also change. Okay, if you change any of the parameters in the corresponding viewing pipeline which we have seen today. So, this is the overall 3D viewing pipeline which talks of a very generalized scenario of viewing, and we have discussed the first 4 stages in a very gross framework, in approximate framework, then we looked into different steps of the 3D viewing pipeline, and finally also we came back into a very exhaustive flow chart about 3D viewing pipeline. Now, what happens, let us say if you don't want to use, let us say in a very simplified scenario, you want to create a very simplified scenario where you know that your camera is aligned with respect to the world coordinate system, you have the objects in front of it and you want to just display the system. Okay, you are not, let us say, but of course if you are involved in using standard graphic softwares, standard graphical packages like Figs and OpenGL, you have to specify, go to this 3D viewing pipeline to display. In most cases they will ask you to specify those parameters, but let us say if you want to write a small program yourself in OpenGL where you will say I'll simplify this entire 3D viewing pipeline and at least the first few stages of normalization and projection geometry of course, and then you will say if I can specify what are my camera parameters in terms of what the view I am looking at, what is the focal length or some parameter for the camera in terms of its lens and screen width and things like that, and what is the view volume I am looking to, can I not transform a point in 3D into the 2D screen? Yes, it is possible. You may not have to go to the entire viewing pipeline to do that, you can use the 3D viewing pipeline, there is absolutely no problem, because it is so general that it can take care of all sorts of transformations, all sorts of scenarios which is possible. But let us say you want to create a simple formula, 1 or 2 steps, let us say, where you know that I have a camera in a virtual reference coordinate system or VRC, okay, view reference coordinate system, situated aligned already with the world, and I have the object in front. Can I pick up the 3D points on the objects and transform it to 2D on the screen? Okay, so we look now in the last few minutes of this lecture today a camera model which gives a very simple formula to transform a 3D point to a 2D point. This is something similar to the projection geometry combined with the transformations. Okay, so what are the, so I am just taking a simple example as a case study where we specify our initial camera model and by identifying the following parameters. So you know what's a scene which consists of polygonal elements each represented by their vertices. So basically you assume for the time being, we have not talked of solid modeling so far, we assume that there are 3D vertices specified in the world and it is in front of the camera, and the camera is also defined by the following parameters, the camera position, maybe it could be the origin of the world coordinate systems, but you can still have Cx, Cy, Cz as the position of the camera. You have a point that represents the center of attention of the camera, or a COA, center of attention, sometimes also called the focus of attention, FOA. In fact, it is true with our eye that we always have a focus, a center of attention to the subject or object we are looking to, and you have a center of attention or a focus of attention for a point for this camera, which is specified also by a point in 3D as Ax, Ay, Az, the components for the coordinates for the point A. And the last important point is the field of view angle alpha. This is something which gives you the canonical view volume type of a scenario. Now you specify that not with planes but a field of view angle alpha, and I will give you the diagram by meaning where is this C, where is this A, what is this alpha, which represents the angle subtended at the apex of the viewing pyramid. Okay, the last point I repeat again is very important, the field of view angle alpha, which represents the angle subtended at the apex of the viewing pyramid. So you need to know C, you need to know A, you need to know alpha, and with these parameters can I take points in 3D which are the vertices of polygonal elements and shift it to 2D. Just a simple projection using these parameters which are there in points 2, 3 and 4, C, A and alpha. points 2, 3 and 4, the parameters C, A and alpha, if they are known, C and alpha are not scalar quantities, they are 3D vectors, and if C, A and alpha is a scalar quantity, it is an angle in degrees or radians, if these three are known, can we come up with a simple projection model. Okay. So, let us look at this scenario. The specification of C and A is given in this figure already. You have an idea what is this alpha? It is the angle subtended at that vertex C, angle subtended at that vertex C of that pyramidal structure. Now, this is similar to a canonical view volume for perspective, and that is the most common and natural model for what is called as a pinhole camera, which is used for image processing tasks as well. When a camera is modeled, of course, there are other parameters, linear and non-linear parameters to model a camera, but this is quite simplified and okay for a computer graphics point of view, where I have C, A and alpha, 3 parameters. And if you look into the figure again, in addition, of course, you will have 2 more surfaces. One is called a near plane and a far plane. Okay, or is also called the front clipping plane and the back clipping plane. You have already known about FP and BP, front clipping plane and back clipping plane, you know, with respect to those 6 surfaces where you are clipping your 3D points and surfaces and lines. So, now this pyramid was infinite. I have made it finite by putting a near plane and a far plane on the front and the back side with respect to the camera, which is looking to the center of the pyramid. You have a center line which passes from C to A being the focus or center of attention of the camera, and the other binding 4 surfaces of the pyramid which define this view volume. So, now what I say is all objects which are inside this finite pyramid, I hope you can visualize this pyramid is infinite pyramid, but putting the near plane or the front clipping plane or far plane is the back clipping plane. If you put these 2, then you have come up with what we will call as a finite pyramid. Okay. And so, the specification of near and far bounding planes must be given, and these planes are considered perpendicular to the direction of view vector. The direction of view vector is nothing but the vector going from C to A. Okay. A is marked here, C is here, okay. A is here. Okay, C to A is the direction of projection, let us say, or it could be even A to C, does not matter, its direction is more important. And these planes, near and far planes, are considered perpendicular to the direction of view vector or direction of projection, DOP. Remember this, and are at a distance n and f from the camera respectively. So, this near plane at a distance n from C. So, the perpendicular distance along the central line which passes from C to A, or the direction of view vector or direction of projection vector, along that line the distance from C to the near plane is n, and from C to the far plane is f. Okay. So, n minus f is the distance along that center of line within the finite view pyramid within which all of these objects must lie to be viewed. You know, clipping will do the operation where any objects which are outside or in front of the near plane, between the camera and the near plane, will not be viewed. Anything which is beyond the far plane also will not be under the view. Okay. Again, the viewing pyramid, the 3D viewing space, again I have just added the coordinate system u, v and w. Of course, you can align the w with the center of line which is piercing to the center of the finite pyramid C to A. You can align the w with that, but it could be very general. You have a near plane, far plane, and the image space view volume is u, v, w, which I will say, although it is 3D, ultimately when you say a 3-dimensional image space with UVW, what you are talking basically is a unit cube at UVW. Okay, unit cube or a unit pyramid, and very simply switch off W, you will get U and V. That is another way. In the case of perspective projection, you switch off W, you get the device coordinates or viewport coordinates or 2D coordinates U and V. But of course, in the case of perspective projection, in which the image space volume is also a pyramidal structure, you need to have a projection matrix switch. So, this is the scenario, and let us see how we can generate the projection matrix for mapping points in 3D onto 2D. This is the side view of the viewing space. I was talking of these distances n and f from the center C to the near plane, and the center is at this vertex bearing an angle alpha, and from the center to the far plane the distance is f. So, this is another side view. I hope the picture of the pyramid is getting clear. This was a 3D picture of the finite pyramid obtained from the infinite structure, which defines the finite view volume, and the image space is also defined in the coordinates on the right hand side. Here in terms of u, v, w, along each axis you have 2, -1 to +1, and this is a 2-dimensional view where I will call it, it could be a side view, it could be a front top view through which you can get this type of triangular structure for the near plane, far plane, and the 2 sides binding along the u, v axis. Okay. Let us go ahead and derive the viewing transformation matrix in terms of the camera parameters. and as we go ahead you note down the equations and the matrices which come along. Let us look at this equation in the figure as given here. You find a point P with coordinates u, v and w, which is projected onto the projection plane at a distance d from the COP. The projection plane is lying in the u, v plane, and the projection point is u prime, v prime, w prime, and you can easily derive u prime, v prime, w prime using similarity of triangles. You have done this a little bit earlier as well, and they are nothing but du by minus w, dv by minus w and minus d respectively. Minus d can easily be found out because the minus w coordinates is minus d. Okay. You can rewrite these three u prime, v prime, w prime as given here equal to du by w, dv by w and minus just the multiplying and dividing by w. So, basically this 3D to 2D is nothing but representing in homogeneous Cartesian coordinate form u, v, w and 1 is transformed to du, dv, dw and minus w, because if you divide the first three coordinates by the fourth one, you are going to get your the 2D coordinates, and which are nothing but your u prime, v prime, and w prime is anyway you know it is equal to minus d. So, once you know, I can write this in form of a matrix, express this as a transformation matrix PD. I can use any one of these forms, diagonally d and then minus 1 in the third element of the fourth column, or you can write this as the identity matrix, 3 ones and the 1 replaced by the 0 in the fourth row, fourth column, but the third element in the fourth column will be minus 1 by t. Either of these matrices could be used, there is absolutely no problem, because you are working in the homogeneous Cartesian coordinate representation. And if you look back into the equation again, you will find that this is a post multiplication. The coordinates in 3D are post multiplied with one of these matrices to get the corresponding u prime, v prime, w prime as given by du, dv, dw and minus w respectively. So, if you look back into the equations, please note down this matrix form and try both these matrices, post multiply a point u, v, w in 3D space, post multiply by PD, any one of them will do, and you will get this. Okay. So, this projective transformation is fine, but you have to work with the view volume. That is, you need to transform the finite truncated view pyramid to the canonical view volume of size u, v, w ranging from minus 1 to plus 1, and we will do that with one axis after another. Let us first analyze the w axis only. Okay. And let us say if you use a transformation matrix, basically it is some sort of scaling and translation which you have to do, and if you use such a transformation matrix where the unknown elements, let us say, are a and b. Why these two? Because this a will handle the scaling along the z axis or w axis. A will handle that and B will handle the transformation projection, also minus 1 you need to provide that. Basically this helps you to transform a point 0 0 minus n multiplied by p to a point 0 0 1, that is the near point will be transformed to the front clipping plane in canonical view volume which is plus 1, and the far clipping plane 0 0 minus f in 3D will be transformed to 0 0 minus 1, that is the back clipping plane. So, if you know that P is able to give these two transformations from 3D to 2D basically, or in fact in 3D itself, then you basically solve for A and B using the above equation. That means you substitute P in these two and you get basically expressions like this. These are the two constants you get for A and B. Remember, N and F are known to you, and you, since you have two equations with two unknowns A and B, you can solve for A and B straight away using these two equations, and you get very simple nice forms as a solution for A and B based on F and N. Remember, F and N are also camera parameters in some sense, because they are the distance to the near plane and near front clipping plane and back clipping plane respectively, the F. Okay. So, let us look back into the matrix. This is the transformation matrix now. This transformation matrix will handle the Z transformation from the finite view pyramid to a canonical view volume. What about u and v with respect to x and y? Well, we have to also go to any one of these axes, and the u v axis transformations of the pyramid are understood by taking the side view again. If I take the pyramidal sidal view, you can see these two white lines are of length. If this is 0 to n and then 0 to f with an angle alpha by 2, because the entire angle is alpha, we are taking half of this pyramid which is alpha by 2, the angle at the vertex. So, these two vertical lines will be of length n 10 alpha by 2 and f alpha by 2. It has to be like that. And what basically happens is, now the points at these two at the edge of the pyramids will be having these 3D coordinates 0 n 10 alpha by 2 and minus n, and this point will also have 0. either u or v we are talking about, and f tan alpha by 2 which is the vertical along u or v, and the z part is minus f. So, these have to be transformed to correspondingly the coordinates 0, 1, minus 1 and 1, that is the desired normalized 3D coordinates for both these points. So, if you employ the matrix P which you have seen, then you get this transformation. You get this transformation from this point n tan alpha by 2 minus n to a transformation matrix like this, and similarly for the f tan alpha by 2, you please note down these equations and try it yourself, multiplied by p, you get this point. Now, you basically need, if you see here, you need to have a transformation matrix P in such a manner that this becomes 0, 1, minus 1 and plus 1, and similarly this also becomes 0, 1, minus 1, and that can be done by modifying P. This can be done by modifying P because the P which we derived with only the z axis had these two terms, f plus, that is the third column, it has these two terms. Now, if you introduce in the diagonal element these two terms cot alpha by 2, it will help you to basically get these two terms vanished, and this will become 0 f minus f and 0 n minus 1, and the transformation will take place basically. Okay. And of course, so you can note down this new form of P using the matrix, and I hope you are able to note it down. The inverse of P, I leave it as an exercise for you to find out, a little bit of matrix manipulation. Try out the inverse of P, which should be this. You can note it down for the time being and practice at home. 4 by 5 matrix, not a very difficult one. This is the matrix P, and this is the inverse of the matrix, which is given as this. The cot alpha has become tan alpha by 2. Diagonal terms are very straightforward, and but the other matrices also will change places. So, the overall viewing transformation matrix, is concatenation, the product of two matrices PD and P, and remember the PD, you can take any one of these two forms D, D, D minus 1 or 1, 1, 1 minus D, and post multiplied by the P matrix which we have just seen. Remember, P is this matrix, and the PD had diagonal elements D and the first 3 diagonals, and it had a minus 1. So, if you multiply PD with that P, you will, the product of the matrix is what you will get as this. One of the forms of PD gives you this, the other form of the PD is what you also basically get in this particular form, and please note down these forms. I am displaying it for you. This is the form of the viewing transformation matrix, and if you look into the parameters, all the parameters are based on the camera model. All the parameters are based on the camera model. If you take D, what is the D? D is something like you can visualize it to be the focal length of the lens, or a camera parameter, where it is basically the distance of the projection plane from the origin, that is the D. What is the alpha? That is the angle subtended at the vertex of the pyramid, okay, which defines your view volume, how much you are looking both sideways and top to bottom. And what are f and n? How much you are looking. You can't look beyond a certain point, and something very close also you cannot visualize properly, which is very realistic. So, you have a front clipping plane distance f, and a far or a back clipping plane distance n, f and n. You have the D where you have the projection plane, you have the alpha. So, all these parameters are there in this projection equation as you see. This is one form of the projection transformation matrix PF, which is PD multiplied by P. If you take the other form of the matrix PD, which is almost singular in identity matrix type 1, 1, 1 and minus 1 by D, you will typically have the nature of the expression of PD in this form. So, kindly note down these two matrices, and I hope if you can start from scratch and derive these matrices expressions yourself, I hope you are able to copy down the expression yourself as given in the slide. Please copy down these expressions and try to derive these from the figures which I have given. I have probably jumped 1 or 2 stages here, steps basically, so that I leave something as an exercise for you to write down matrices from the expressions directly, because you have gone through 2D transformations, gone to 3D transformations, gone through projective transformations, gone through viewing pipeline, and now given equations you should be able to write in matrix or matrix back to equations, do the manipulation, and again the most important thing is to visualize what these transformations mean, because these transformations are nothing but basically implementing a graphical scenario from you for the user, for the viewer, and you must know why these transformations are very important. You will have algorithms in graphics, all right, but the mathematics part is also very, very important, which you cannot, and along with that the geometrical interpretation which you must have in mind. So, we will wind up this lecture today on 3D viewing pipeline with this set of, we have in fact discussed about general transformations of viewing pipeline, which consist of 4 broad stages: applying normalized transformation, clipping to canonical view volume, use the projection matrix, and then actually scale and translate into viewport. These were the 4 broad stages. We discussed the second normalize in the last lecture, the normalizing transformation, which had 5 different steps, correct? Rotation, translation, shear, scale, and finally a rotation, scale again at the end. And those were the 5 different steps for the normalizing transformation, which helped you to bring the view reference coordinate and the entire objects, align them with respect to the world coordinate system for proper viewing. Then of course you need to scale it down to the canonical view volume or 3D viewport, clip, have the clipping done, which we'll discuss later on, and then of course do the perspective projection from 3D to 2D. That was the general viewing pipeline. And then of course we went to an example case study where, what about for a simplified situation? If let us say only camera model parameters are given, is it possible to generate a view? Yes, it's possible. You can bypass, if not necessary, the entire generalized 3D viewing pipeline, and if the camera parameters are given. What are the camera parameters given? The D, which is the distance of the projection plane from the center of the camera, the angle subtended by at the vertex alpha, which defines the pyramidal view volume, and N and F, the distance of the front and back keeping plane. If these are given, these parameters are given, you can define also come up with a projection transformation matrix, which will take you from 3D to 2D. We have seen the last 2 expressions in 2 different forms, almost similar expressions which take you from 3D to 2D and without in fact going to the extensive pipeline. But you must also know the extended viewing pipeline, which helps you to understand a generalized scenario which all graphic standards and packages mostly follow. So when you are using standard graphics packages and softwares and graphical standards, let us say the fix is an example which we have been following in this course very extensively. We have not come up with specific examples, but we will devote 1 hour at least for certain examples of FIGS and OpenGL together. When you need to follow such graphic standards, you have to follow a 3D viewing pipeline. You cannot. But of course, you want to write a small software or interface which is based on simple camera parameters or camera models. Yes, what you can do basically is use such a transformation matrix and get the transformation done from 3D to 2D, which includes the canonical concept of even canonical view volumes and helps you to even clip if necessary. Okay, so that is the last slide, and we wind up this lecture, end of the lectures on 3D viewing, projective transforms, and viewing pipeline. Thank you very much.